Welcome to our group's presentation on SKEL 3212. Today we teach you about CoWoS packaging or chips on wafer on substrate. So for decades, the semiconductor industry had relied on Moore's law. By shrinking the transistor size, we are able to fit more power in the single monolithic chips. However, we have hit a physical wall. The chip sizes are too large for us to manufacture. To solve this problem, TSMC have developed CoWoS. So today's we discuss about the CoWoS architecture, its trade-off, and 5 recent papers discussing about the physical limitation of CoWoS. For the CoWoS architecture overview, we could see that it had 3 layers. For the top layers is where is our logic circuit will be. It could be GPU logic, it could be CPU logic, or it could be for AI users. And for the middle part is where the magic happens. It is the silicon interposer, usually routed by TSV or RDL. And for the third layer, we have the substrate. So the connection between the logic layers and the interposer layers is usually the microbump. And for the interposer and the substrate interconnection, usually we are using C4 copper bumps. So why do we use 3 layers? Silicon interposer act as structural stress buffer, meaning that during a high thermal condition, the interposer act as a provide mechanical support. TSVS allowed for vertical power and data routing, meaning that the data and the power can be driven through the hard silicon layer. And the organic substrate translate the microscopic pitch into standard size so that it could be fit on the motherboard.
So my name is Chan Chung Kang. Now I'm going to talk about the comparison between the monolithic system on chip with CoWoS architecture. In the monolithic system on chip, all functions are integrated on a single silicon die. And in CoWoS, multiple chiplets and HBM are integrated on an interposer, which enabling the heterogeneous integration. Thermally, monolithic system on chip have relative uniform heat distribution. And in contrast, CoWoS introduced a hotspot and thermal bottleneck due to uneven power distribution across the chiplets and the memory stack. And from an interconnect perspective, system on chip use on-chip wiring, while CoWoS rely on advanced package-level interconnect like RDLs, microbumps, and TSVs. And finally, scalability is a key difference. System on chip are limited by the reticle size, while CoWoS enable the scaling by combining the multiple smaller dies into a single package. So the main trade-off is clear. CoWoS improve the scalability and the performance, but introduce a higher thermal and packaging complexity. And next, we're going to talk about the challenge in the CoWoS. As we move to the CoWoS and the cheaper system, thermal limit become a major challenge. First, the power density can exceed 3.5 kilowatts in the modern AI accelerated, which leading to a strong localized hotspot across the chiplets and the HBM stack. And second, the thermal bottleneck occurs because heat spread easily in plane through the interposer, but vertical heat removal is limited by the low conductivity material like underfused and the dielectric. And third, the CTE mismatch between the silicon and the organic substrate create a mechanical stretch, which leading to package warpage and the reliability degradation. So to address this issue, two cooling approaches are used. First is about the cool pad cooling, and the second one is the micro-channel cooling. So for the cool pad cooling, use a liquid cooler metal plate attached to the package, and this is suitable for the high-power AI system. And for higher heat flux, the micro-channel cooling embed the fluid channel diary into the substrate or interposer, bringing coolant closer to the hotspot and improving the heat removal efficiency. And next is about the reliability challenge. The material complexity in the heterogeneous integration lead to the mechanical stress because different material expand the differently under the temperature change. Besides, the high density micro bumps also increase alignment difficulty and failure risk. And this factor contribute to failures such as delamination, solder fatigue, and the warpage. And the traditional reliability testing is also limited because it provides only the pass or fail result and cannot capture the multiple interacting failure mechanism. So to solve this, the modern approach uses the physics of failure to understand the root cause, along with the building from ground up framework, in situ monitoring, and advanced diagnostic. So overall, the reliability engineering is shift from simple testing to the predictive, physics-based analysis. So now I'll pass to my next teammate.
And now I'll be discussing paper 4. So traditionally on the PCB, the path between the logic and the memory is so long that it introduces a high capacitive and inductive loading, meaning that the signal will be delayed and it causes a massive power dissipation, create also a memory wall for AI workload. So CoWoS solve this by utilizing local silicon interconnection and submicron redistribution layers using around 0.4 microamp each. This means that the signal stay entirely within the highly conductive passive silicon, and this eliminates the transmission losses and drastically lower the energy per bit transferred.
Hi, my name is Tang Hongyi, and I'm going to do a literature review regarding the reliability simulation analysis of the SV structures in silicon interposer under temperature cycling. as CoWoS technology used silicon interposer, which containing true silicon wires or TSVs to connect multiple chips together. During operation, especially in the AI accelerator and high-performance computing system, the package repeatedly heat up and cools down. The problem is that copper TSVs and surrounding materials such as silicon, silicon dioxide, and redistribution layer have different coefficient of thermal expansion. As a result, thermal stress develop during temperature changes. Over time, this stress can cause cracking, delaminations, and reliability failure. To investigate this problem, the researcher developed the finite element 3D model as shown in this figure, which closely represents an actual CoWoS package's structure. The researchers uses finite element simulation to evaluate the TSV reliability. As shown in the figure, this model subjected to temperature cycling between 85 degrees Celsius and negative 55 degrees Celsius. This condition followed the industry reliability testing standard. While the simulation was repeated for 3 cycles to observe how the thermal stress accumulates over time. The objective was to identify the most critical TSV locations and determine how the thermal cycling affect the long-term reliability of the interposer. So this figure shows the equivalent stress distribution during the low temperature state. The red regions indicates the highest stress concentration. The researchers found that the TSV RDL interface experienced the largest stress, reaching approximately 190 megapascal. This is significant because the stress concentration often becomes the starting point of the crack formations and fatigue failure. Another important finding is that the TSV located at the center of the interposer, as we can see the red color here, experienced the greatest stress, making the most vulnerable locations in the packages. While another figure shows the maximum equivalent stress changes during the temperature cycling. The stress increases and decreases with temperature, but more importantly is that it gradually accumulates over successive cycles. This indicates the presence of thermal fatigue. Based on the simulation result, the estimated fatigue life of the TSV structures is approximately 317,000 cycles. Therefore, to analyze the strength of these papers is that it includes realistic interposer layers and manufacturing defects, making the result more representative of the actual CoWoS packages. As the researchers uses 3D finite element simulations, by modeling exact where the stress concentrates, the engineers can alter the distance between TSVs and adjust the electroplating parameters on a computer, completely preventing the interconnects from breaking before the physical manufacturing even begin. However, the study is limited to simulations and does not include experimental validation. Overall, this paper demonstrates that the TSV RDL interface are critical reliability bottlenecks in a CoWoS packaging. Understanding this failure mechanism can help engineers design more reliable interposer for futures AI and high-performance computing application. That's all from me, and now I will pass to my another member.
Hi, Doctor. I'm Owen. This paper is focused on the bottleneck in AI, HPC, and the cloud data transmission. So traditional copper interconnection suffering on the communication in signal attenuation, electromagnetic interference, and high power consumption. To solve the problem, the author suggested a solution which using the CPO, which is the photonic integrated circuits. PIC are integrated closely with the electronic integrated circuits. The architecture supported by a heterogeneous integration technology, which is the fan-out wafer level packaging, FOWLP, through silicon valve, TSV, through glass valve, CGV, and with the optical waveguides and edge couplers and the PCM technologies. And these are the mechanism which can help us to reduce the power consumption and improve the bandwidth density and provide a scalable packaging solution in future high-speed communication system. In summary, the chip-on-wafer on substrate is an advanced 2.5D package technology is helped to solve limit of traditional system-on-chip design. It works by combining multiple chips such as processor and high-bandwidth memory into one package. This is done by a silicon interposed through the silicon valves and the micro bumps connection. And because of this structure, the chip-on-wafer on the substrate can achieve a high bandwidth, low delay, and better power efficient, widely used in AI, high-performance computing, and data center. Compared to normal system-on-chip, the chip-on-wafer on substrate is more flexible. It allows the different type of chip made with different technologies to work together in one system. However, there's still a challenge such as heat management, reliability of TSV, and high production costs. In conclusion, the chip-on-wafer on substrate is important technology that support the modern computing and help continue performance growth beyond Moore's law. That's all our presentation. Thank you.